Okay, this is the second part of section 3.5, solving inequalities with absolute value. Okay, so this time we're going to focus on inequalities. So not equals, inequalities. Okay, so to start off, let's kind of picture a number line because that's usually the best way to think about inequalities. And you know how number lines work. You have negative infinity off to the left. To the right, you have positive infinity. And then in the middle, you have all your numbers that you're used to. So let me put a few here. Right, so we know how the number line works. Okay, well, if you saw something like the absolute value of, let's say, 2, or absolute value of x is greater than 2, well, what could that mean? All right, what could that mean? Well, that could mean that inside of here, let's say greater than or equal to 2. Absolute value of x is greater than or equal to 2. Well, that means you're kind of solving this equation, right? The absolute value of x equals 2. That'll take care of that equal part. And then a few other equations like absolute value of x is equal to 3 and 4 and so on. Right? That's what this means. Absolute value of x is greater than or equal to 2 means I want to know what x would have to be for for the absolute value to be 2, for it to be 3, 4, and so on. And then all the numbers in between, like 2.5 and so on. Okay? Well, if you think about it, well, what could this be? If you think about the last section, x could be 2, or x could be negative 2, right? Those are both possible. If I plugged a negative 2 in right here, it would equal positive 2. So we'd say, okay, 2 and negative 2. Well, what about this one? X could be 3, or x could be negative 3. X could be 3, x could be negative 3, plus all the stuff in between, right? So like 2.5, negative 2.5, and so on. 4, negative 4. It seems that our solution would involve everything to the right of 2, right, where everything is greater than 2, and everything to the left of negative 2, where everything is less than negative 2, right? If I took, say, I don't know, way down the line, negative 10, well, the absolute value of negative 10 equals a positive 10, which, of course, is greater than 2, right? So let's generalize that rule. We have two sets of our solution here. Let's generalize it a little bit. So first of all, just like the last one, we're going to talk about our value being positive, right, greater than 0. Okay, if the absolute value of x is greater than or equal to a, it could be greater than or equal to, right? That just doesn't matter too much. If the absolute value of x is greater than a, our positive number here, then we have two scenarios. X is greater than or equal to a, or x is less than or equal to negative a. Okay, so in other words, as long as you have a positive number here, like we did 2, you have two scenarios. You have the first scenario to the right, and you have the second one to the left. Anything in those two areas will be valid solutions. Okay, so that's for these greater than solutions. Okay, and by the way, if you wanted to be technical here, what about if it's greater than a? Okay, well then x is greater than a, or x is less than negative a. Okay, so that technically covers both options there. Okay, anyway, not a big deal. Something you could keep in mind, by the way, is if you notice it's a greater than symbol, if you decide you want to change the way you spell greater to be spelled this way, great or, then you'll remember that it's this one or this one. Okay, maybe keep that in mind. It's a good way to differentiate that one between what if this is a less than symbol. So let's talk about less than. So let's draw our number line again. And again, we know how number lines work. 0, 1, 2, 3, 4, -1, -2, -3, -4. Okay. And let's say this time we're trying to solve the absolute value of x is less than or equal to, let's say 2 again. Okay, so this is different, right? Because here we're interested in absolute value of x equals 2, and then values that are less than 2, like 1 or 0, maybe, right? We don't want to worry too much about the absolute value being equal to a -1, right? Because what does that make sense? How does that make sense? It doesn't, right? Remember, the absolute value has to equal a positive number here, not a negative. Okay, think back to last section when we talked about that. Okay, so, well, what are our options here? X could equal 2. X could equal -2. Okay. X could equal 1. X could equal -1. X could equal 0. And you could say something about -0, but does that really make sense? -0 is just 0, so we'll just leave that part off. Okay, so we have 2, -2. We have 1, -1. We have 0. If you threw in a fraction, let's say 1/2 or 0.5, you would have positive 0.5 and negative 0.5. So notice the difference here. This one is not one that goes off into the infinities, right? That would be the greater problem, the greater than problem. Instead, you have this enclosed space here that starts with -2 and ends with +2. Okay, so let's generalize that idea. In this case, we're actually interested in two different things. Okay, when x is less than 2, which would be all of that, and x is greater than -2, which is all of that, we care about where the x values on the number line is both less than 2 and greater than 2. So that's going to be where these two lines overlap each other, right? It's everything in between. Okay, so that's how the less than problems are different. All right, so let's generalize that idea. Of course, again, we're dealing with a being greater than 0. In other words, positive. If the absolute value of x is less than or equal to a, then x is less than or equal to a. And I'm going to use the word and, right? Remember, because I care where the x's are both less than or equal to a and greater than or equal to -a. In other words, where they overlap each other, because it's going to be an enclosed space. Okay, so that's the big difference there. And remember, I promised different words to help you remember. Think less than. Okay, adding a letter there. Spelling it wrong, again, on purpose. So and means where do they overlap, right? Think overlap. Or think either or, right? Where either this line is or this line is. Both are part of the solution. All right, so we're going to do some examples in just a second so we can kind of really solidify the idea. But let me just, for the sake of having this all neat, I'll say, what if it's just less than? Then exactly the same thing, except with less than symbols. Okay, let's jump to some examples. First example here, let's solve, very simple. The absolute value of x is greater than 7. Okay, so with this problem, let's graph the solution and let's also write it in interval notation. Okay, we'll do that in a second. So this is a greater than problem. This is greater, right? Greater. So we'll say or x is greater than 7 or x is less than -7. Let's graph that out. And you don't have to draw it perfectly, right? You can just put -7 here and +7 here. We know those numbers are between -infinity and +infinity, so as long as you put them in the right order, you're good. In other words, don't put a +7 and a -7, right? That would not make sense. Okay, so x is greater than 7. Use red for that, greater than 7. So x cannot equal 7, so we use our open circle here. And we say go to the right, because that's where you're going to find all the greater than 7s. Let's use blue for -7. X is less than -7. It's not equal to -7. So again, open circle. Everything to the left would be our less than -7s. Okay, so there's our graphical answer. Finally, let's write it out in interval notation. Okay, if you remember interval notation, I'm going to look at these two segments here. Here's the first one. I'm going to write it out, -infinity to -7. In parentheses, right? The left parenthesis, because you always have one on infinity. The right parenthesis, because we have an open circle. Okay, union, the right side, this red piece right here, starts at 7 and goes until infinity. So that would be our solution in interval notation, which is usually how we want to put our answer. Okay, so that was interval notation. I won't write this every time, but this is interval notation. This is graphical notation. And this is technically called algebraic notation. Okay, in case they ask you to specify. Okay, I don't think they will. Let's do another example, a little bit more complicated. Okay, the absolute value of 5x is less than or equal to 4. Okay, right away, I'm going to identify this as a less than problem. So in other words, it's an and problem. So my solution set is going to have the word and in between, and I'm going to think overlap. Where do they overlap? All right, so 5x is less than or equal to 4, and 5x is greater than or equal to -4. Now this is just like in the last section. I took whatever's inside here and did the same thing I ordinarily would if it were just an x. Okay, and so that gives me two simple inequalities. Divide both sides by 5, so that's going to be 4 over 5. X is less than or equal to 4 over 5. And at the same time, x is greater than or equal to -4 over 5. Okay, let's graph that. -infinity, +infinity, -4/5, +4/5. Okay, the first one here, I'll do in red. X is less than or equal to 4/5. Okay, so it can equal 4/5, so I'll put a closed circle there. Less than would be to the left. X is greater than or equal to -4/5. Excuse me. So it can equal -4/5, so I'll put a closed circle. And greater than means I'm going to the right. Okay, since this is an and problem, the question is now where do they overlap? And they overlap here, starting at -4/5 all the way to +4/5. Now, because I used closed circles, I have to use brackets instead of parentheses. There's only one piece, and it goes -4/5 to +4/5 in brackets. Okay, so that's the difference between an or problem and an and problem. Let's do another one. Okay, let's see. Yeah, example 3. We have the absolute value of 3x plus 4 is less than 13. Okay, less than, this is an and/overlap problem. Okay, the inside, 3x plus 4 is less than 13, and 3x plus 4 is greater than negative 13. Okay, two inequalities to solve. Subtract 4 from both sides. 13 minus 4 is 9. Divide both sides by 3. 9 divided by 3 is 3. And subtract 4 from both sides. Negative 13 minus 4 is negative 17. Divide by 3. X is greater than negative 17 over 3. Okay, so there we go, and a problem. So I need to find where these two will overlap. Negative 17 over 3, not 4. And 3 go here and here. All right, I put the negative on the left, the positive's on the right. Okay, x is less than 3. Can't equal 3, has to be less than, so open circle to the right. X is greater than negative 17 over 3. Open circle, because it can't equal negative 17 over 3. And go to the right. All right, and problem, so where do they overlap? Well, from here to here. And I'll keep those open circles. So negative 17 over 3 is where it starts, parenthesis for the open circle. 3, parenthesis for the open circle. Okay, so that would be the solution set for this one. All the numbers between negative 17 over 3 and positive 3. Let's do two more examples. This one's a little tricky. So we have the absolute value of 2x minus 1 over 3 is greater than or equal to 5 over 6. So before I panic about the fractions, the first thing I'll do is recognize that this is greater than, so this is an or problem. So think either or. All right, so 2x minus 1 over 6 is, over 3 is greater than or equal to 5 over 6, or 2x minus 1 over 3 is less than or equal to negative 5 over 6. Okay, first thing I want to do is take care of the fractions, okay, all of the fractions. So I'm going to actually multiply both sides by 6, okay, because that's the common denominator out of 3 and 6. So multiply this side by 6, multiply this side by 6. And of course, I'm going to do the same thing here, so I might as well write it. 6 divided by 3 is 2. So really, this is just 2 times 2x minus 1 is greater than or equal to 6 divided by 6 cancels out. I'm left with just 5. Distribute the 2. It's going to be 4x minus 2 is greater than or equal to 5. Add 2 to both sides. Divide by 4. So x is greater than or equal to 7/4. 6 divided by 3 is 2. The 6's cancel out here. 2 times 2x minus 1 is less than or equal to negative 5. Distribute the 2. Add 2 to both sides. Divide both sides by 4. So 7/4 and negative 3/4. Of course, with the word or in between. Okay, so let's graph it out. Okay, negative infinity is here, positive infinity is here. Negative 3/4 is on the left, positive 7/4 is on the right. So x is greater than or equal to 7/4. Since it can be equal to, I'll put a closed circle. And greater than's off to the right. -3/4, or x is less than -3/4, or equal to, so we can equal it, put a closed circle. That's going to be to the left. Okay, and since it's an OR problem, they don't have to overlap, right? They don't have to overlap. So I can just write them out as I see them. On the left, -infinity to -3/4. We said there's always a parenthesis on -infinity, or infinity in general. But since there's a closed circle on -3/4, I will put a bracket, union, bracket on 7/4, and it goes until infinity, so positive infinity. There's our solution in interval notation. All right, I want to do one more example, if you can even call this one an example. Absolute value of 3x plus 5 is less than 0. I want to solve that inequality. Okay, but of course the trick is, remember we said that it had to, that this number here, right, this is our a value, it had to be positive. Well, 0 is not positive, right? It's neutral. It's not positive, it's not negative. So there's no solution. Another way you can think about this, to help it make a little bit more sense, remember, the absolute value of something will always be a positive number, or 0, right? It can't equal a negative. There's no way that can happen. Absolute value always gives you a positive number, never a negative. So how can something be less than 0? How can an absolute value be less than 0? It can't, right? Can't happen. So therefore, this one has no solution. Okay, and so that is the second part of section 3.5, solving absolute value inequalities.